Good afternoon, welcome to VTU EduSat. Today's topic in analog electronics is continuation of FET amplifiers. Today we will look into other topology of FET like common gate configuration, and also we will look into the cascade configuration. The main objectives of today's lecture are students should be able to perform AC analysis of common gate configuration, know its characteristics. At the same time, when in multi-stage amplification, what happens to the AC parameters can also be understood. In the previous lecture, we dealt with one of the topology of FET, that is source follower. Now, we did the AC analysis also. Now, let us take an example to know how AC parameters can be computed for a common source configuration. So, the problem statement is DC analysis of source follower network shown results in VGSQ is equal to minus 2.86 volts and IDQ is equal to 4.56 milliamperes. So, the Q point at Q point the value of gate to source voltage and drain current are specified. For this, it is required to determine the AC parameters. AC parameters like transconductance GM, drain resistance RD, input impedance ZI, output impedance Z0 with and without drain resistance. Finally, it is required to evaluate what is voltage gain with and without RD. Now, first let us look at the circuit. In the circuit, there is a source resistance connected between source node and ground. The value of this RS is 2.2 kilo ohms. A gate resistance is connected from gate to ground. The value is 1 mega ohms. Input is applied between gate and ground. Observe the drain terminal. Drain terminal is connected to VDD. So, obviously, this is a source follower network. The reason being, for AC analysis, we will be reducing this 9 volts to 0. That is, this ground is drain is grounded. So, drain becomes common between gate and source. Another notable fact is output is taken across the between source and ground. That is, the output is node is from source to ground. So, it is a source follower circuit. Apart from this, some more FET parameters are specified, like IDSS value is given, VP and YOS. Now, let us see how we can evaluate all these AC parameters for this given circuit. So, RG is 1 mega ohms, RS is 2.2 K, this is drain which is tied to plus 9 volts, this is VI, and across source we are taking out the output. Now, we have derived the expressions for various finding out the AC parameters for common drain configuration. So, using those expressions and the given values, we should be in a position to find out what will be the values of all these parameters. So, first thing is we need to find out GM. GM is given by GM naught into 1 minus VGS divided by VP. Now, VGS is given, that is VGSQ is given to be minus 2.86 volts, and even IDQ is 4.56 milliamperes. This is the given data. Now, in this expression, VGS is known, VP is given to be minus 4 volts, IDSS is 16 milliamps and YOS is 25 microseconds. So, the values, these are the given values. Now, find out GM. So, to find out GM, first we will be determining GM naught. GM naught is given to be 2 IDSS divided by magnitude of Vp. So, 2 times IDSS is 16 milli divided by Vp is 4. So, by evaluating this, we find that it is 8 millisiemens. Now, find out GM using this expression, that is 8 milli into 1 minus the value of VGS is the value of VGSQ specified, which is minus 2.86. So, minus 2.86 divided by value of Vp is minus 4. By evaluating this expression, we find that the value of GM is 2.28 millisiemens. The next parameter to be determined is the value of RD. To determine RD, the output equivalent admittance value is given, that is YOS. Take the reciprocal of this YOS to determine RD. So, RD is 1 by YOS. So, which is nothing but 1 by 225 into 10 power of minus 6. So, which comes to around 40 kilo ohms. Next is to evaluate input impedance. So, in the previous lecture, we have found that the input impedance Zi is nothing but the value of Rg. So, Zi is equal to Rg, which is equal to 1 mega ohm. The value of Rg is specified to be 1 mega ohm. Next is to find the value of output impedance. So, output impedance you need to evaluate by considering Rd and even without Rd. By considering Rd, that is with Rd, we had derived the expression to be Rd parallel Rs, Rd parallel Rs, which in turn is in parallel with 1 by Gm. So, in the previous lecture, we had derived this expression. By considering Rd, we find that Z0 is given to be Rd parallel with Rs parallel with 1 by Gm. That is, 1 by Z0 will be equal to 1 by Rd plus 1 by Rs plus 1 by Gm. So, find out this and take the reciprocal to finally obtain the value of Z0, which is 362.5. Now, since the value of Rd is large in comparison with Rs, so since Rd is too large, so we can a parallel combination of Rd with Rs will be approximately equal to Rs. So, Z0 without Rd is Rs parallel with 1 by Gm. So, Z0 will be equal to, if we do not take the effect of Rd, it will be equal to 1 by Gm parallel with Rs, that is Rs into 1 by Gm divided by Rs plus 1 by Gm. So, this comes to around 365.9 ohms. So, just observe the difference in the value of Z0 we get by considering Rd and by without considering Rd. So, there is marginal difference. So, if we consider Rd, output impedance will be low. If we do not consider Rd, it is slightly on the higher side. Next parameter is to evaluate AV, voltage gain. So, voltage gain is given to be equal to GM into RD parallel with RS divided by 1 plus GM into RD parallel with RS. So, this is the expression what we get if RD is considered. Now, substitution of these values in this expression will give the value of GM, value of AV with RD to be equal to 0.826. So, as you know that AV is the ratio of output voltage to input voltage, it is unitless. Now, without RD, let us evaluate what is voltage gain without RD. So, if we do not consider RD, then the equation becomes GMRS. Since RD is very much greater than RS, RD parallel with RS approaches RS. So, GMRS divided by 1 plus GM into RS. So, by evaluating this, we find the value of AV is around 0.833. So, there is a marginal increase in the value of AV if we do not consider the effect of RD, as you can note down by the value. And moreover, common drain, in case of common drain configuration, voltage gain should be less than 1, which we are getting in this case. So, it can never be greater than 1. So, input impedance will be on the higher side, output impedance will be low as it is expressed in ohms, which we have got here in this example, and voltage gain is also on the lower side, it is less than 1, which can a maximum of up to 1 can be attained using common drain configuration. Now, let us look into the next topology of FET, that is common gate configuration. So, in common gate configuration, gate terminal must be common between the source as well as the drain. So, the circuit is shown here. So, as you can see, gate is grounded directly, source between source and gate input voltage Vi is applied and output is taken between drain and ground. So, for establishing the biasing, RS is included in between source and ground, RD along with the biasing voltage VDD is connected between drain and ground. So, common gate configuration exhibits low input impedance, moderate output impedance and moderate voltage gain. Now, let us perform the AC analysis of this topology. To perform AC analysis, first we need to obtain the AC equivalent circuit. So, AC equivalent circuit can be obtained by shorting C1 and C2 and reducing VDD to 0. Now, the resultant circuit will look like this. So, between source and ground, RS is included, between drain and ground, RD. Since VDD is to be reduced to 0, it is represented by a short circuit here. So, across RD, we will be taking out the output and we will be applying the input between source and ground. So, this is the AC equivalent circuit. So, the next step in AC analysis is to write the small signal equivalent model for JFET. So, we all know the small signal model. First, we will write the small signal model here. So, between source and gate, there exists VGS. Then, between drain and source, there is a voltage current controlled source with the direction of arrow from drain to source. The value of this controlled source is GM into VGS, and then between drain and source we also have the drain resistance, that is RD. So, this will give you the small signal model. Now, to this small signal model we will be adding the other external components, that is RS. RS is connected between source node and ground, gate is directly grounded, then RD appears between drain node and ground, and here we are taking out V0. Here we are applying Vi. So, this is the small signal equivalent model of common gate configuration. So, next I will just rearrange this circuit so that it will be easy for us to find out input impedance and output impedance. So, input impedance, when we look back at the circuit from the input node, now since RS is connected between the source and the ground, we need to calculate the another input impedance, because we need to evaluate what is the equivalent of this input impedance. Only then we should be in a position to find out Zi. Output impedance by looking at the output node. Now, let me call this node as A and this node as B. Let this voltage drop be Vi prime. Now, I will be rewriting this. This is source node, this is drain, this is RD, and here between drain and gate I am having RD, and this is node A. Now, to find out Zi dash we will not be considering RS. So, this is Vi dash is now the input. Between source and gate you are having VGS, between source and gate there is VGS. Now, value of this is GM into VGS. Let the drop across RD be called VRD and drop across RD be called V capital RD. Now, let this current be I dash. So, let this obviously this current will also be I dash. Now, by looking at this circuit we can directly write Vi dash is nothing but minus VGS. So, Vi dash is nothing but minus VGS. Look at the polarity here, we are considering Vi dash to be positive here, but for VGS it is negative. So, Vi dash will be equal to minus VGS. Now, to find this we will apply KVL around the loop. So, it is Vi dash minus VRD minus V capital RD is equal to 0. So, Vi dash minus VRD minus I dash into RD is equal to 0. So, VRD I want to find a value for express VRD. So, VRD is given to be Vi dash minus I dash into RD. So, the reason why we are finding out this VRD is Zi dash is nothing but, if I want to look back here at the circuit, Zi dash will be Vi dash by I dash, that is total voltage, the input voltage divided by the total current, which is nothing but Vi dash by I dash. So, I need to obtain an expression in this form so that we can determine on what parameters Zi depends on. Now, I will apply KCL at node A. So, I dash is inflowing in and even GM VGS is moving towards A. Only thing is that the current through RD, which I have called IRD, is leaving that terminal. So, I dash and GM VGS will have positive polarity, whereas IRD will have negative polarity. So, I dash plus GM VGS is equal to IRD is nothing but VRD by RD. So, IRD is nothing but the drop across RD divided by the value of RD. Now, VGS is also equal to minus VI dash. So, I dash minus GM into VI dash, substitute for VRD from this expression. So, VI dash minus I dash RD divided by RD. Now, group all VI dash terms. So, VI dash will be 1 by RD plus GM. This is equal to group all I dash terms. I dash into 1 by RD by RD plus 1. Now, we want VI dash by I dash. By rearranging this expression, we find that this is equal to RD by RD plus 1 divided by 1 by RD plus GM. So, if I take out RD as common, we find that it is RD plus RD divided by 1 plus GM RD. So, this is the expression for ZI dash. Now, to find out ZI, we will have to replace this part of the circuit by ZI dash. Across ZI dash, we are having RS. Now, total input impedance will be nothing but the parallel combination of RS and ZI dash. So, RS parallel with ZI dash. So, we know what is the equation for ZI dash. If we substitute it here, we will get it. So, if we ignore the value of RD in comparison with RD, since RD is very much greater than RD, the above expression can be written as RD, right? You will get RD. So, ZI will be equal to if you ignore it, you will get a much smaller expression. Next is to find out the output impedance. So, output impedance can be determined by looking at the output node when Vi is reduced to 0. So, when Vi is 0, there exists a short circuit across RS. So, RS becomes redundant. So, RS will not have any effect on Z0. The only thing that is left out is this GM, VGS and RD across it and RD here, and this point is grounded. So, Z0 is nothing but the parallel combination of RD with RD. So, Z0 is RD parallel with RD. So, it is approximately equal to the value of RD, since RD drain resistance is too large in comparison with the external drain resistance. So, coming to voltage gain. So, I will take the current through RD to be ID because it is flowing in the drain node. So, V0 is nothing but the drop across RD, that is ID into RD. AV is the ratio of V0 by Vi. By looking at the circuit, we can write V0 to be ID into RD. Now, we need to find an expression for ID, that is express ID in terms of Vi, so that we can evaluate what is AV. So, to do that, we will be applying KCL at node B. That that is this node, ID is flowing into it, GM VGS is leaving it, then ID I'll treat it as from plus to minus because we have treated V naught as positive. So, obviously current will flow from the higher potential to lower potential. So, it is leaving the node B, even GM VGS is leaving the node B, even IRD is leaving the node B. So, all these three currents will be added. The sum of all these three currents should be equal to 0. GM VGS plus IRD is equal to 0. Now, the polarity of voltage drop across RD is indicated here because the direction of flow of current will be from higher potential to lower potential. Now, I will express VRD in terms of VI and V naught. To do that, apply KVL to the outer part of the circuit. So, we will get VI plus VRD minus V naught is equal to 0, or VRD is nothing but V naught minus VI. So, IRD has to be expressed in terms of VRD and the value of resistance. So, that is the reason we are finding out the expression for VRD. Now, VGS is nothing but the value of VI. So, VGS is equal to minus VI. VGS is equal to minus VI. VI is applied across RS and we are taking VGS between source node and gate. Gate is also grounded with a opposite polarity. So, VGS is nothing but minus VI. Now, substitute these expressions in equation 1. ID minus GM into VI plus VRD by RD is equal to 0. Now, we will substitute for VRD, ID minus GM into VI plus V naught minus VI by RD is equal to 0. Now, we will rearrange this expression so that ID can be obtained. So, ID will be equal to GM VI minus of V naught minus VI by RD. Substitute 4 in equation for V naught, that is V naught is equal to ID into RD. So, V naught will be equal to GM VI minus V naught minus VI by RD into entire thing has to be multiplied by RD. Now, we will group all V naught terms. So, V naught into 1 plus RD by RD, I will take out this term, then this is equal to VI into GM plus 1 RD by RD. So, for finding out AV, we need the ratio of V naught by VI. Rearranging this, we will find V naught by VI is nothing but GM plus RD by RD divided by 1 plus RD by RD. So, if I take out RD, then GM RD plus RD divided by RD plus RD. We will arrive at this expression. So, GM RD plus RD divided by RD plus RD. Now, we know that RD is very much greater than RD. So, I can write RD plus RD to be equal to RD. So, under this condition, we can write AV to be GM into RD. So, this RD I have missed out, GM into RD it is. So, you will get RD into RD. So, GM RD. So, this RD gets cancelled with the denominator term, so that you will arrive at GM into RD. So, we find that the input impedance for this is low. On the other hand, the output impedance is moderate, and we find that our voltage gain is also moderate. It is not equal to 1, unlike common drain configuration. To illustrate this, we will take the example of a common source circuit. The value of VGSQ is minus 2.2 volts and IDQ is 2.03 milliamperes. For this data, we need to find out the AC parameters. So, IDSS is 10 milliamperes, Vp is minus 4 volts, YOS is 50 micro, then Vi is 40 millivolts, VGSQ is minus 2.2 volts, then IDQ is 2.03 milliamps. So, GM naught, to find GM we need to find out GM naught, which is nothing but 2 IDSS by Vp, magnitude of Vp, that is 2 times. If you substitute the value of IDQ and Vp, we will find that it is equal to 5 millisiemens. Then find out GM using GM into 1 minus VGSQ by Vp. So, VGSQ value is given to be minus 2.2 volts. So, we have to consider the polarity also in finding out. So, this comes to around 2.25 millisiemens. Next is RD. To find out the RD, take the reciprocal of the output admittance. So, this comes to around 20 kilo ohms. Next, you need to find out Zi. So, it is given that you have to find out the value of Zi with and without RD. So, without RD, Zi is nothing but Rs parallel with 1 by GM. So, which we have found just now. So, without RD, Zi is given to be Rs parallel with 1 by GM. So, by substituting these values, we find that it is around 0.35 kilo ohms. So, coming to with RD. So, we have evaluated the expression to be Zi dash parallel with Rs. So, Zi dash is nothing but RD plus RD divided by 1 plus GM RD, this entire thing in parallel with Rs. So, by evaluating this, RD value you will come to know by looking at the circuit, it is around 3.6 K. Rs value is also equal to 1.1 K. So, by substituting this, we find that the value of Zi becomes 0.31 kilo ohms. Z naught is RD parallel with RD. So, if we consider RD, then it is RD parallel with RD. So, this comes to around 3.05 kilo ohms. So, without RD, obviously Z naught is same as that of the value of RD, which is 3.6 kilo ohms. So, observe the difference here. So, without RD, Zi is around 0.35 kilo ohms. If we consider the effect of RD, we find that the input impedance has decreased. So, even with respect to output impedance, if we consider the effect of RD, it is 3 kilo ohms. If we ignore the effect of RD, then we find that it is increased to 3.6 K. So, on similar lines, we have to find out what is the value of AV. Without RD, it is GM into RD. So, this comes to around 8.1. So, on the other hand, AV with RD, we have to use the expression which we have just now derived. So, which is nothing but GM RD plus RD by RD divided by 1 plus RD by RD. So, substituting the values, we find that gain with RD will be lesser than what we get without RD. So, it is around 7. Now, the last part of the problem is it is required to determine V naught with and without RD. So, determination of V naught is very simple because value of Vi is specified, and we have also calculated what is voltage gain. So, from fundamentals we can write that AV is V naught by Vi. So, V naught will be AV times Vi. So, AV is without RD. Use the value of AV without, which we have evaluated without RD, that is 8.1 times. The value of Vi is 40 millivolts. So, this comes to around 324 millivolts. On similar lines, calculate what will be the value of V naught with RD. So, this is AV with RD into 40 millivolts. So, with RD we found the value of voltage gain to be 7 into 40 millivolts, which is around 280 millivolts. So, this example shows that the input impedance of common gate configuration is low, output impedance is moderate, it can go up to a maximum of the value of RD, whereas voltage gain is also moderate, it is greater than 1, and look at the polarity of AV, it is positive. So, which indicates there is no phase shift between input and the output. So, to summarize, common gate configuration exhibits low input impedance, moderate output impedance and moderate voltage gain. Now, coming to cascade, till now we were discussing the different topologies of JFET. So, in all these analysis have considered JFET as the FET. So, we can replace JFET by MOSFETs also. So, if you are using MOSFETs, you can go for either depletion type MOSFET or enhancement type MOSFET. Depletion type MOSFET analysis for any FETs are same, only difference lies in the equation of drain current. For depletion type MOSFET, the same drain current holds good, that is ID is equal to IDSS into 1 minus VGS divided by VP the whole squared. Only for enhancement type MOSFET, the drain current equation is different. So, if enhancement mode MOSFET are used, we can write the ID value can be determined from ID is equal to IDSS into VGS minus VT the whole squared. So, this is the only difference. So, the analysis methodology what we have followed, the same methodology applies to even MOSFETs. Coming to multi-stage configuration, that is, if till now we have been dealing with only single stage amplifier, that is only one FET with the respective biasing networks were used to perform amplification process. Suppose further amplification is essential, then we may have to connect the output of the first stage to as the input of the second stage, so that we will get an enhanced gain. So, the resulting configuration is called cascade configuration. So, this is first stage, input is applied to first stage, then output of first stage, this is the input of first stage, output of first stage, let me call it as VO1, is applied as input to of the second stage. Then output of second stage will be the final output if you are going for two-stage amplification. So, in multi-stage amplifiers can have more than two stages. This is just an example wherein which only two-stage amplification is illustrated. So, this type of connection is called cascading. So, we are cascading a second stage to the first stage. Now, what will happen to the AC and AC parameters of such amplifiers, such multi-stage amplifiers? So, in such situations, we will the input impedance of the overall cascaded configuration will be that of the input impedance of the first stage. So, Zi is the total input impedance. This is nothing but the input impedance of first stage. Output impedance of the cascaded configuration will be the output impedance of the second stage. That is, if I call Z0 as the overall output impedance, then Z0 is the Z0 of, if Z0 of second stage is ZO2, ZO2 it will be the output impedance, overall output impedance. Then what about the gain, overall gain of the cascaded configuration? So, overall gain AV can be denoted as the product of voltage gains of individual stages. So, if I call AV1 as the voltage gain of the first stage and AV2 as the voltage gain of the second stage, then the total voltage gain of the cascaded configuration will be product of voltage gain of the first stage as well as the second stage, that is AV1 into AV2. Now, while evaluating the voltage gain, we need to find out what is the loading effect of the second stage on the first stage. So, there will be some input impedance offered by the second stage, there will be some output resistance offered by the first stage. So, the overall loading at the first stage is the combination of these two. So, if they appear in parallel, it will be R0 parallel with Ri2. So, that will be the output impedance of the first stage. So, while performing cascading configuration, first stage could be either common source, common gate or common source follower. On similar lines, second stage could be any other configuration of amplifier. So, we have to look at the configuration used, accordingly find out AV1, perform ISC analysis to find out what is input impedance, what is its voltage gain and output impedance. On similar lines for the next stage, and using these analysis we can estimate what will be the overall input impedance, overall output impedance and the total voltage gain. To illustrate this, let me take one example. So, this is a given circuit. There are two stages in this circuit. It is required to calculate the voltage gain, input impedance and output impedance as well as the voltage gain for the cascaded configuration shown here. So, first stage is a common source amplifier because source lead is common between the input as well as its output. RS value is 680 ohms. Since RS is included in the circuit, obviously this is a self biasing method used. RG value, RG1 is 3.3 mega ohms, and second stage is also a common source amplifier. Both are identical, as you can make out the value of RDs, RS, RG are same, even the values of ID, SS and pinch off voltage is also same. So, for this we need to evaluate what is the total voltage gain, input impedance, output impedance, and even the voltage gains of individual stages. Now, let us see how we can approach this problem. Stage 1 has Rg1 is equal to 3.3 mega ohms. The same is the value of Rg2, that is stage 2. Now, Rs1 is 680 ohms, Rs2 is also 680 ohms, Rd1 is 2.4 kilo ohms, this is also Rd1. Now, for this we need to find out what is AV1, AV2, overall voltage gain, then you have to determine what is input impedance and output impedance. The FET parameters are specified, that is IDSS value and VP value is given. So, IDSS is 10 milliamperes, VP is minus 4 volts. So, you can determine GM naught into 1 minus VGS divided by VP. So, VGS value is specified. So, let us consider VGS to be around minus 2.2 volts. For this value you find out the value of GM. So, once GM is found out, now we can find out what is AV. So, how we can determine AV? Look at the circuit, there is a bypass capacitor connected across Rs. So, the analysis will be similar to that of fixed bias analysis. So, voltage gain will be equal to minus GM into Rd. So, minus GM into Rd parallel with Rd. So, Rd is not specified, let me assume Rd to be infinity. So, we will get AV to be minus GM into Rd. By substituting the values, so GM is around 2.6 millisiemens, you can find out the value of gain of the first stage. So, this is around minus 6.24. So, on similar lines find out what will be the gain of the second stage. So, second stage is similar to that of the first stage. So, AV2 will also have the same value, that is minus 6.24. Next is the output input impedance. So, input impedance of the cascaded configuration will be the input impedance of the first stage, which is nothing but Rg value. So, Zi is equal to Rg1, which is nothing but 3.3 mega ohms. Z naught will be that of the output impedance of the second stage, that is ZO naught. 2, since it is a common source amplifier with bypassed capacitor, it should be equal to Rd parallel with Rd. So, since Rd is equal to infinity, so this will be equal to Rd, which is nothing but Rd2, that is 2.4 kilo ohms. So, the value of output impedance of the cascaded configuration is 2.4 kilo ohms. So, since we have found out AV1 and AV2, you can evaluate what is AVT. Overall voltage gain is nothing but the product of the two voltage gains. So, if you multiply 6.24 into 6.24, you will get it to be 38.4. So, we just now evaluated what will be the overall voltage gain, input impedance and output impedance in case of cascaded configuration. So, one thing is, while finding out the voltage gain of the first stage, we have to consider the loading effect of the second stage. The loading effect of the second stage will be, this is Rd, that is 2.4 kilo ohms, Now, there is Rg appearing at the input side. So, while performing AC analysis, we will reduce this Rd to 0. So, it is as good as saying that Rd will appear across 3 mega ohms. So, this Rd parallel Rd is nothing but in fact 2.4K parallel with 3.3 mega ohms. So, this equation, this value you have to use here in order to find out the value of the voltage gain of the first stage. So, in cascaded configuration, we have to consider the loading effect. That is what we can understand from this discussion. So, in today's class, we have performed the AC analysis of common gate configuration, wherein which we found that the input impedance is low, output impedance is moderate, voltage gain is also moderate, there is no phase shift between output and input, and we also looked into how we can estimate the input impedance and output impedance as well as overall voltage gain of a cascaded configuration. Thank you.